Hello students, welcome to Continuum Mechanics. Today we're going to do a special lecture on tensors, where we're going to review the key concepts, of what a tensor is and how we go about defining different types of tensors. So in our previous lecture we talked about vectors. We introduced the key concepts. We talked about the dot product, the cross product, and so on. And we know that vectors are useful. Vectors are things such as the direction. They indicate direction vectors, or position vectors, velocity, acceleration, force vectors. There are many different quantities in continuum mechanics that we use that are vectors. However, there are other more complicated quantities with more information in them that we must define as tensors, right? So this lecture is all about detailing what a tensor is and the different types of tensors. Now, some examples of tensors that we will see in this class are, of course, the Cauchy stress tensor, right? Our nice stress tensor, which we define as a 3x3 matrix. Our Lagrangian strain, which is also a 3x3, as well as our stiffness tensor, which is a 6x6 matrix. Right? So it's 3x3, and this is a 6x6. So we need to be able to distinguish, well, what is the difference between these 3x3, Cauchy stress, and Lagrangian strain, and why do we have a tensor that is a 6x6? So let's start with the basic definition of a tensor. A tensor is a matrix that is linear, homogeneous, and a vector valued function. And each of these descriptions give us the mathematical relationships and the laws as it relates to tensors. So let's start with the latter, vector valued function. A vector valued function is a tensor that acts on a vector and produces a vector as a result of the operation. So if we have some input vector and we perform an operation with a tensor, our output, or the product, will be a vector v. So if we have an input vector and we perform an operation with our tensor, we end up with a output vector. So we're going from a matrix. We're performing an operation with a vector, and our output is a vector. Hence, vector valued function. Now, homogeneous. Homogeneous of degree 1 means that a function has the following property. That if we take that tensor and we perform an operation where there's a scalar multiplied by a vector, that scalar can actually be pulled on the outside of that operation. It can be pulled out and be performed at the end of all operations. And subsequently, when we remember this relationship, or when we bring this relationship here down, we find that we have the scalar times our output vector, where alpha is just a scalar quantity. So this is a key property that allows us to do a lot of mathematical manipulation with our tensors. Now, lastly, is the question of how do we define if our tensor is linear. Well, if our tensor is linear, then that means if we have a series of vectors, that this series of vectors can be separated into individual operations. Meaning, if we have our tensor and we have two vectors, a vector, an input vector 1 and input vector 2, we could change the order of our operation, meaning separate these into two operations. And we should note that our brackets, they indicate the first operation that we would perform when we're when we're actually executing the math, right? So we're saying that if we have a vector f, which is going to be multiplied by input vector 1 and 2 that are added together first, and then multiplied, well, then we can say that we could do those operations separately, where we could multiply our vector f by each of these inputs and achieve the same result. And of course, this also indicates that we could define two output vectors from this operation, right? So we have this linear behavior observed in our tensor here. Now, when we go and combine both the homogeneous nature as well as the linear nature of our tensor, we'll find the following behavior. We'll find that if f tensor is operated with a scalar alpha times a vector u1 plus a scalar beta times the input vector u2, then we could separate, we could actually do this operation in a different order, so we could commute out our alpha times our tensor f times u1 plus beta times our tensor times u2, and then subsequently we could say that this is all equal to, alpha v1 plus beta vector v2, right? So these rules here and these relationships really help us to evaluate our tensors. All right. So again, let's remind ourselves that we say that a tensor is something that if we have an input vector and we perform an operation with respect to our tensor, that we achieve some output vector. So this property, if we have an input times a tensor and we get some output, suggests that the operation, the multiplicative operation that we're producing here, would be the tensor dot product our input vector. So generally, our output vector will have a different magnitude and direction to that of our input vector, typically. So the direction is different, and the magnitude itself, so V is not equal, the magnitude of V is not equal to the magnitude of U. Now there is a special case where the input and output vectors are identical. we have our, we're doing the dot product for input vector with respect to our tensor. If they are identical, then we arrive at a tensor, capital I, where that tensor I is the identity tensor, such that that dot product operation produces the exact same vector. Now let's remember from our previous lecture the dot product of a vector to a vector. Say we have a vector A and we perform the dot product of it with respect to a vector B. Then that product, that multiplication with a dot, will give us a scalar where A times B, where A and B are the magnitude, times cosine theta is the product of that operation. Now the dot product of a vector to a vector is commutative in the sense that if we switch the order B dot product A, we will produce the same scalar quantity because the angle between the vectors doesn't change. Right? We're simply switching the order, right? So then let's go ahead and apply this to our little tensor relationship here, and let's introduce another vector W by which we do this dot product. So let's say we do W dot product V. What will we result in? Well, we'll result in that the vector W dot product, the tensor F dot product, the vector U, right? And if we remember the commutative law or the commutative rule for vectors to vectors, remembering, hey, this is a vector, we can switch the order, right? If we wanted to. Right? If we do that, then we can simply say that our vector W dot product vector V is also going to be the same thing as W dot our tensor F dot U, meaning that the first operation in this equation, or in this equation, does not matter. We can change what operation we perform first. We will produce the same overall outcome. So the order of the operation no longer matters, and we can simply drop the parentheses and just say, hey, the vector W dot V is just the vector W dot tensor F dot vector U, right? And we can perform any operation in any order we want and produce the same overall outcome. Okay, well then what about if we wanted to perform the dot product of a tensor to a vector, right? So what we've been doing here, remember we've got V is equal to F dot U, right? Well, what we'll find when we do the dot product of a tensor to a vector is that that operation is not commutative. So this operation cannot be easily switched, the order switched. And as a result, we'll find that the tensor F dot product of U is actually equal to U, the dot product of the tensor F transposed. So instead of actually being commutative, we actually find a tensor that is transposed. With this transpose operation, let's note transposed here. So this little t indicates the operator. Well, let's note that if we have a vector, if we have a tensor f, that tensor in index notation is Fij, and if we were to transpose that tensor, then the order of the indices changes, meaning that f becomes Ji. So in essence, we are switching the off-diagonal terms. So F12 becomes F21. They switch positions, those off-diagonal terms. With these relationships, it then follows that if we have V dot the tensor F dot the vector U, then we can replace this with U dot F transposed dot V. So in essence, it's not a simple commutative relationship. It is not commutative. Instead, we introduce the transpose to switch that relationship. And this, again, all we're doing is replacing this with this relationship here, right? So from this, we can define the idea of a symmetric tensor and an antisymmetric tensor. So a symmetric tensor is a tensor with elements where the tensor f is equal to the transpose of that same tensor. What this means is that Fij is equal to Fji. Switching the off-diagonal terms, switching the F12 with F21, they have the same value. They're equal to each other, so switching them doesn't do anything. It doesn't matter. It's a symmetric tensor. While we also can find the idea of the antisymmetric tensor, where if we have a tensor f, it is antisymmetric if it is also equal to the f transposed times -1, right? Meaning that the magnitude of the terms that are on the off diagonal are equal, but they have opposite senses, right? Now the cool thing is that if we have a tensor which is linear, homogeneous, and a vector valued function, then we can separate every tensor that meets those rules into a symmetric portion and an antisymmetric portion. So we have a if we have a tensor f, we can find a symmetric portion of it, which is 1/2 of f plus f transposed, and we can find an antisymmetric portion, which is 1/2 the tensor f minus the tensor f transposed. So we end up with our symmetric portion and our anti-symmetric / skew portion of this tensor. All right. So now let's go ahead and try to deal with the idea of inverting a tensor. So some tensors, under certain conditions, are possible or have the capability to be inverted, meaning we have the capability of going from an operation where we start with an input vector, we perform the dot product operation on the tensor, and we produce an output vector v. Well, for some tensors, we can do the opposite, or we can reverse the process and find the input by inverting our tensor and performing the dot product with respect to the output vector, right? In some cases. Now, We'll learn later on the specific rules required for an invertible tensor. But for now, let's try to identify a relationship that tells us if our tensor is invertible, or tells us something about invertible tensors. So let's remember our identity tensor. Remember that if we have an identity tensor, then the input vector and the output vector are equal to each other. So u is equal to I dot product u. Well, if we take our first equation, our equation here of the idea of an invertible tensor, and we take this identity tensor, replacing that term on the left-hand side, and we take our original idea of this output vector and placing it on the right-hand side, we can arrive at this relationship where our identity tensor dot product, our input vector, is equal to our inverted tensor dot product, our tensor f dot product, our input vector. So we're simply replacing the u with the identity dot product u, and we're replacing the v with the tensor f dot product u, right? So now we've got this nice little relationship here, and we can rearrange this, collecting everything to the left-hand side to produce the following. Or moving the left-hand side term to the right, we'll find that 0. Well, let's do it this way. We'll find that the f inverse dot product tensor f minus the identity tensor with respect to our u vector is equal to 0. So we've collected all of the terms, moved everything to the left-hand side, or we'll move everything to the right-hand side, setting it equal to 0, and then collecting the u vector all together, right? So collecting our terms. We end up with this nice relationship here, the f vector, the f tensor inverse dot product the f tensor minus the identity tensor, all of that with relation to our vector u, right? Now the beautiful thing about this is that we can further simplify this by eliminating our u term. If u is not equal to 0, then in order for this function to be true, in order for this function to be true, then we must have an invertible tensor. So we can define that an invertible tensor has the following property: that the inversion of that tensor times the dot product of its original form is equal to our identity tensor, which is a great relationship for us. Very great relationship for us. Now it can be difficult to by itself, this function is can be difficult to solve, particularly if we have higher order tensors. There's too many unknowns. But it's a very useful property that we will exploit later when we're dealing with deformation. So now let's look at the idea of an orthogonal tensor. What is an orthogonal tensor? So, if the input vector, v, has the same magnitude as the output vector, but its direction is different, then the tensor operation results in a rotation. Meaning we have some direction vector, we perform an operation, and the direction changes, we've performed a rotation, right? Makes sense. So let's say that we have some tensor A. We perform a dot product of that tensor with respect to our input vector, and our output is a vector that has the same magnitude but a different direction. So then if we do the dot product of these vectors, so say we did the dot product of v with respect to itself, well, we know that that would be v, the magnitude of v times the magnitude of v times the cosine of 0, which gives us v squared, right? Similarly, if we did the u dot product of u, we get u cosine of 0, which is equal to u squared. Well, if the magnitudes of these vectors are the same, then we can say that the dot product of v dot v is equal to the dot product of u dot u. So v squared is equal to u squared. Now, why are we doing this? We're saying they have the same magnitude, but the directions are different. So if we did v is equal to u, that wouldn't work. Their sense is not the same, but the magnitudes are the same, right? So where are we going with this? Well, let's remember some properties. Let's remember some useful properties that will allow us to move forward. Well, we remember that the dot product of a tensor with a vector is not commutative, and in order to complete, instead of being commutative, we arrive at the relationship where the vector dot product the transpose of the tensor is equal to the original form. We also want to remember that if we have an operation where a tensor is multiplied by a vector and we get the same vector, then we have an identity tensor, right? Okay, so let's use these two properties, and let's use our rotation tensor A, and let's see where we go with this. Okay. All right, so we have v dot v is equal to u dot u. Let's use that dot product of the let's use the dot product of the tensor with a vector. Let's use that on the left hand side here. So let's replace this v with u dot product A transposed, and the dot product of that being A dot u, right? So we're simply using both sides of that tensor vector dot product, right? Okay, and on the right hand side, let's use our identity, and let's replace one of the u's with the identity. So we'll have this u dot the identity dot u, right? Now, if we look at this equation, we can see some similarities across it. Even though we have these brackets which indicate the first operation, we know that these vectors, this is a vector and this is a vector. The dot product is commutative, right? If it is commutative, we can drop our brackets. We don't need those first operator brackets. So in essence, we have on both the left and right hand side u surrounding these tensors. So with that knowledge, let's keep these here. Let's keep these here. But with that knowledge, knowing that the brackets are not necessary, and knowing that if both sides are to be equal, we could use any vector u in this equation and produce the same relationship, well, then we can pull out our tensors here. And we'll find that the transpose of A dot product A is equal to our identity. So if we have an orthogonal tensor, this relationship here must be true, right? Now let's continue and let's look at principal values. So it's possible to find an input vector u such that our output vector v has the same direction but a different magnitude. So this is another side of the coin here, right? So in essence, what we're saying is, so we have an input vector, and we perform some operation to change the magnitude, such as multiply it by a scalar. We can find a vector v that has the same direction, but its magnitude is different, and it's different by the value of our scalar quantity, lambda, right? Now, if we do this, then we can, and we consider, remembering that the tensor f dot product, the input vector, is equal to our output vector. Well, if we pull this relationship in, we'll find lambda u is equal to f dot product u, right? So there's this scalar quantity in our vector u, which is related to our tensor dot product, our vector, right? Now with this knowledge, if we move everything over and set it equal to 0, we'll find, and collect the like terms, we'll find that f minus lambda times an identity tensor is equal, times u is equal to 0, right? Well, our 0 is a 0 vector field with zeros, right? So we found this nice little relationship here where there's this term lambda, there's this vector u that relates to our tensor f. So there exists special values of lambda and u, special values of our scalar and our tensor, our vector, our vector u, where the vector u does not equal to a vector 0, right? So there actually exists special vectors where u itself does not equal to 0. And there's a relationship between this and this that produce that 0-valued vector, not just u itself, the actual terms in it being equal to 0. And these special values of lambda and the vector and vectors u are principal values called the eigenvalues mathematically, and are principal directions called our eigenvectors. And we'll find that the magnitude of our eigenvector is equal to 0. When we solve for the magnitude of that vector, not equal to 0, equal to 1, right? The magnitude of our eigenvector equal to 1 in that relationship. And later on, we'll go into the details of finding these. In our previous class, we kind of went over it in terms of stress, finding the principal stresses and directions. We'll do that again later on, but for now, let's continue. So now let's look at the idea of defining what the order of a tensor is. So it's important to note that the tensors we've introduced here today are second-order tensors. And they're called second-order tensors because they input a vector and they output a vector. And we can define an nth-order tensor as the following. If we have a tensor of the nth order, and we do the dot product with respect to a vector, our output will be a tensor at a lower order, n minus 1. And so from this, we can subsequently say that a tensor of order 0 is equal to a scalar, a first order tensor is a vector, and a second order tensor is a second order tensor. Right? Makes sense. Second order tensor times a vector gives us a vector, f1, right? A vector, right? And from this, we can subsequently find that there are higher order tensors. There's third order, fourth order, and so on. So we get closer to the idea of where does what do we consider our stiffness tensor, right? It's a higher order tensor, right? So that is the lecture for today. Hopefully you find this new approach to our notes where we're using the arrows to underline our vectors and tensors more useful. We'll continue with this approach and continue to have a fun time in continuum mechanics. In our next class, we will be doing Cartesian coordinates, and we will also be moving into looking at the vector cross product. All right, that's the end of class for today. Thank you for your time and attention.